So, last time we saw the proof of the remarkable theorem, or the Theorem Is True, as it passed into history with its Latin name. Gauss was writing in Latin at his time. So, actually, this is of course not the formulation I gave you in the last lecture, because what is written here contains the statement, the important statement we saw last time, we proved last time. So, the Gauss curvature of a regular surface is invariant by local isometries. This is the most elegant way you can phrase it. But how do you prove it? How did we prove it? By saying it's invariant by local isometries, we actually proved that there exists a formula, doesn't matter how complicated, I mean, especially if you compare it with the standard one. This is definitely more complicated, so why should you choose this one? Well, this one is definitely much more interesting in some sense, because it shows that this expression, which depends on the first and the second fundamental form, actually, by a little miracle, depends only on the first fundamental form. So, okay, it's a horrible expression, but it involves only the coefficients of the first fundamental form. And the first fundamental form is invariant by isometries, so this formula is invariant by isometries. Okay? Quite rarely we will use this formula to actually compute it. Well, it depends what kind of geometry we are doing. Especially this points out to a general language difference in geometry between extrinsic and intrinsic geometry. So when you use the extrinsic word, it means you are thinking of your surface inside something else, and you are looking to your object from outside. That means you are using the second fundamental form. The second fundamental form requires the normal vector and the derivative of the normal vector. So it means you are looking from outside. While the intrinsic thing means you are playing the intellectual game of being an animal living on this object, on this space, and being able to do only the things that an animal living on this space can do, which in particular means, in our kind of geometry, measuring distances between points and angles between directions. That's the first fundamental form. Okay? So intrinsic versus extrinsic formulation. Okay? So, well, as I said, I mean, okay, a few comments. I mean, this is, of course, an extremely important theorem. So, I mentioned to you the idea of Riemann of taking this as a kind of a definition for higher dimensional spaces, for higher than what are called Riemannian manifolds. But we will talk about that later on in the course. So, well, first, this points out to many, I mean, now we can go in many directions. First, let's take the simplest thing. Okay, this is an horrible formula, but it actually simplifies it a lot when you have a special set of coordinates. So the difficulty in this formula points again to always to the same problem. Remember, in the case of curves, the problem of coordinates was solved in lecture 1, arc length. Okay? On a surface, we are still looking for something which we can call the best set of coordinates on a surface. Okay? We don't have it. We saw many things. I'll come back later to this point. But let's first just see this formula where it's pointing to. So, for example, in particular, if you have a set of coordinates for which the first fundamental form becomes simpler than usual, so, for example, suppose you can actually make the first coefficient equal to 1, constant equal to 1. So these are functions on your chart, okay? So not just at the given point, but also around the point. And suppose, so this means the vector xu has constant norm 1. And suppose also that you can actually make xu and xv orthogonal everywhere. So the uv coordinates give you a set of orthogonal coordinates in such a way that the first one is always of norm 1. Now be careful. If I also put g equal to 1, it's game over. it's the plane. Well, it's isometric to the plane. Could be the cylinder, could be something else, but it's the first fundamental form of the plane. But suppose you reach this point, then actually the formula simplifies greatly. So K, and this is actually one formula we will use. So now the only free parameter is this the last coefficients of the first fundamental form, G. So this becomes G to the minus 1/2 second derivative in du squared of G to the power 1/2. That's one way to write it. And there is nothing to prove. Just put E. If E is equal to 1, of course, all this term disappears because you are taking the derivative of E. And then if E is equal to 1, this becomes just square root of G. This just becomes square root of G, and then you just get the formula. Okay? So, of course, yeah. Okay. This is just. So this is an interesting particular case, which points actually to the problem of whether we are able to actually produce a set of coordinates for which these conditions are true. Okay? We will come back to that later. So, before moving into this direction, of course, this theorem, let's go back for a moment to the statement of the theorem equation. In the elegant form, the theorem equation, let's repeat it. It says the Gauss curvature is an invariant by local isometries, because this is a local computation. You don't need a global isometry. You don't need the two surfaces to be, for example, homeomorphic or diffeomorphic. You just need it locally to have an isometry between these two things. If you have a local isometry between two surfaces, then at those points, the Gauss curvature is the same, is invariant. So one natural question is whether also the converse is true. Suppose that you have two surfaces for which the Gauss curvatures are the same. I mean, is this an if and only if? Are the two surfaces isometric? Okay, that would be fantastic, of course, because remember, the problem of detecting whether two objects are isometric, it's a huge problem, even locally, besides all the topological and the general problems. So, unfortunately, the answer is no. And I left my notes in the office. Okay. I don't remember by heart. The examples are not. Okay. Okay, that means I will put it in the homework. Okay. What does it mean the converse does not hold? The converse means there actually exists two surfaces, locally isometric. Oh, sorry, two surfaces. Such that, actually, for example, two surfaces which are, in fact, in the examples you can produce, these two surfaces are, so S1 is actually X1 of U. So these are globally parameterized by one chart, and S2 is actually X2 of the same domain U. Okay, so now I can compare the first fundamental forms, the Gauss curvatures, everything, because these will be functions over the same domain U, such that K1, so K of the first surface, the Gauss curvature at P is equal to K2 of P for any P in U. So they have actually the same Gauss curvature at every point, but it does not exist any isometry phi . Not even locally. I mean, don't play just with the game of taking two things which are not homeomorphic. I mean, that doesn't count as a counterexample. Okay. Okay. I'll put at least one example in the homeworks. Okay. They are not easy because, of course, it's not too hard to produce examples with this property, but then how to prove that the two things are not locally isometric, then it's a bit more delicate, because you can, in principle, the fact that you compute anything you compute in these charts and they turn out to be different, this doesn't prove anything, okay? Because you need to prove that something cannot be achieved. Okay. So the Gauss curvature is not an if and only if in terms of the invariance of the Gauss curvature is not equivalent to the isometric problem. Okay, it's just implied. Just one quick historical remark. This is actually where Gauss stopped, and actually this had strange enough, I mean, the Theorem Egregium was actually the end of an historical important problem. At that time, one of the main applications of this kind of study was the problem of producing the perfect map, cartography. Okay? It was the time where ships were going into oceans around the world and people were just dying because they didn't know where they were. So producing the map was actually the king of Norway or Denmark, I never remember, set up a huge prize for a mathematician or for a scientist who could produce the perfect map. So what does it mean, the perfect map? What do you ask for a map? Well, the map should be a faithful representation of the Earth, of course, scaled down. Okay. Now, besides the problem of scaling down, which is obvious, then what does it mean? What are you trying to do? You are trying to find an isometry between the sphere, or at least a piece of the sphere, a local isometry between the sphere and the plane. That's a mathematical formulation of the problem of the perfect map. Okay? Well, that's what Gauss claimed to have solved. In the negative. Is it possible to produce the perfect map? No. Why? Theorem Egregium. The Gauss curvature of the sphere is constant positive. The Gauss curvature of the plane is 0. So there is no isometry. If there was an isometry, you apply the Gauss theorem, and then they have to have the same Gauss curvature. Okay. So there is no perfect map. Any map is wrong. So then you have to decide how wrong you want it. You want it in terms of distances between points, you want in terms of angles between directions, you want both, you want to make a mistake in both things, but controlled in some way, and so on. Okay? So this was also historically important for this thing. I mean, this was still the time where this kind of mathematics was developed by very practical problems. Okay, so the practical problem behind this was this. Okay, so now let me go back to this point. So the problem of the best set of coordinates. I mean, so remember, we have seen now a few classes of maps, of charts. So, of course, we have maybe I can put just a little table here. Isometries between plane, a piece of the plane. Now, when is a chart an isometry? Or conformal, or, for example, area preserving, and actually we can go on. So we did this preserving. Okay, so area preserving, do you remember what it meant? It meant, remember the measure we used to compute integrals, to compute areas of domains. So this actually meant EG minus F squared constantly equal to 1, because the square root of this function is actually the weight of the measure that we are using. Conformal meant you don't stretch angles. Actually, this is connected to the problem of the perfect map. Because now, for example, now that you know that there are no isometries, you can decide that you don't care whether a map is faithful in terms of distances between points, but maybe for you it's more important that the angles that are on the maps are the same as the angle on the Earth. In fact, I would prefer a map like this. I don't care if I measure the distance on the map between Trieste and Milan. If I get a number which has essentially nothing to do with the real distance, but I want to know at which angle do I have to turn to get to Milan. I don't care if it takes 3 hours more, but I want to go to Milan. Especially if I'm in the middle of the ocean, I want to reach land, even if I reach it tomorrow. Okay? So conformal was particularly important also for this, turned out to be. And conformal, what did it mean? It means that the set of coordinates are actually orthogonal. So f equal to 0. And then the two things, the two standard vectors, xu and xv, actually have the same norm at every point. So, okay. Okay, of course, but isometries is the combination of everything. So these are all kind of the best, in some sense, depending on the problems we are facing, these are all the best set of coordinates we saw. Now, let's make a further step. On the other hand, we have seen, I mean, not many examples, but I mean, we know that they exist only under special circumstances. I mean, okay, you cannot expect every time to be able to produce this. So now we are driving to a general existence theorem. How can we produce on any surface something which we can call the best set of coordinates? Okay. So to do that, we actually take a long path. And actually, we are going to study a problem which is not directly the problem of the best coordinates. We want to study another problem which will solve everything at the same time. And in fact, the problem is also, again, very natural. In some sense, what I told you up to now is a quite technical problem. And now let's go back to something that anybody, not even a mathematician, could ask you. I mean, if you are an expert on surfaces, let's think of this problem. You pick 2 points, P and Q, and you look at the set of curves joining these 2 points. Okay? So I will draw any curve here, let's say gamma or alpha, starting from P and going to Q. Okay. Now, among these, the question is there a better one, a best one? And of course, which is the only thing you can do with a curve is measuring the length. So what would be the best curve? Well, the best curve should be the curve of minimal length joining 2 points. So which is the curve? The basic question is, how do you produce? After all, in Euclidean geometry, we know that this is a rather interesting thing to do, no? Because we know what you would get. Given 2 points, you would get the segment. So can we, in some sense, speak about the segment on any surface? Okay. So let's formalize everything mathematically. And let's see. So gamma is a curve. So actually, I should have drew it here, but here, because it's a map. And let's decide that the domain of the curve is always some closed interval AB. Okay? P and Q are fixed. And now, definition. First of all, a family, I don't care really about one single curve at the moment. I really want to take one curve and move it in a family. So what do I mean by a family of smooth curves? On S, well, actually, it's nothing but a family of smooth maps, but has to be smooth, required to be smooth also in the parameter direction. So not just every time it's a smooth curve, but also the way they depend on the parameters. So that's just, let me call it capital gamma, since the elements will be. So let's say there is a parameter moving even in some small interval, I don't need much. And then all curves will be parameterized by the same closed interval AB with values in S. Okay? And then I require smoothness, which means smooth in both variables. Okay, so now it's a function of two variables, of two real variables. So a little bit of notation. Of course, why do I call it a family of curves? Because every time I fix the parameter, let's say that I will always call T yeah, so S is a parameter here and T the parameter here, okay? So every time I fix S, gamma of S dot, okay? So this is, I will actually call it gamma S, okay? So this will be the curve at parameter, I would like to think, I have two times. I have the time along the curve and I have the time along the perturbation on the curve, okay? So at time S. So this is, of course, is a smooth curve because it's the restriction of a smooth map to a line. So, and now, so again, definition. Gamma, one single curve, is called geodesic if for any smooth family gamma for any smooth family which starts from my little gamma. So what do I mean by that? Such that gamma of 0 dot, so what I call gamma 0 is actually my original curve gamma. So for any, basically I can rephrase by saying for any perturbation of my curve gamma which actually preserve the initial and final points. So gamma such that this is a perturbation and gamma S of A is equal gamma of A. So the initial point is always the same and the final point is always the same for any S. So how do we have to think of this? So this is a kind of a family of curves, but they all start from the same place and end up in the same place. Okay? And in the center of this family, there is your initial curve gamma. Okay? So if you are in this situation, then what can you do? You can compute the length of each of them for any S. So now this is what? This is a function of S. For any S, I compute the length. So I will be interested in those curves for which the derivative of this function at S equal to 0, of course, because I care what's going on here along the central curve, and this is 0. Okay? Note that I introduced the problem by saying I'm looking for a curve of minimal length. And actually I wrote something much milder. I just wrote the fact that the curve, this curve, a geodesic, will be a critical point of the length. Okay? I have to phrase it in this kind of elaborated way because, of course, the space of, I could say, I want to look at the length functional over the set of curves, joining this point and this point. And then I can say, well, does this functional has a critical point, as a minimum, as a maximum, and so on. The only problem is the set of curves joining 2 points is a rather complicated object, even topologically. I don't know how to put, in some sense, it's not even clear how to put a topology right away on it. So then if I phrase it, if I want to phrase it, and actually this has been done, of course, about a century ago, but how to phrase it in terms of functional analysis? Well, the first thing I need to build is some kind of metric space or Banach space of the set of curves which join 2 points. So with the topology and so on. So this is a bit elaborated. I prefer not to do it now. So this is a way to bypass. I'm saying it's a critical point on every possible family. So then, of course, this is going to be kind of hard to check, okay, whether a curve is a geodesic or not, because in principle, I should produce any possible deformation and then prove that this condition is satisfied. We will see how to bypass it. In fact, actually, the way to bypass it is the first thing we have to face, because how does this equation look like? I mean, what is this really asking from the curve, on the curve gamma? I need a lot of space, so I can also erase my little table. The idea is always the following. Well, let me draw it, because it's always the same picture, but at least I find it very convenient to draw it. It's always the same. So you have your curve, gamma, and actually, let's suppose, in order to understand what this is condition saying, let's suppose that this is actually contained in a chart, and let's see inside the chart, what kind of equation is this? Okay, so suppose here you have your famous x and your famous u and so on. That means that actually gamma comes from somewhere here, and then we will write the corresponding equation here in the plane. Okay, so let's do it. So under these assumptions, okay, if everything is contained in xu, okay, let's decrypt this equation. That means what? That gamma s of t, so each of these curves is actually x of what? Of u. Well, I would say of u, but also u is a function of 2 variables. No? For any s, I have a curve. Okay. Now notations. Let me write them here. The t derivatives, so du, because now I have to start taking derivatives with respect to t or with respect to s. So let's fix some notation. I will call this with a dot. Okay. And also, let me write, there is always a function coming in, so let me give it a name. I will call it capital R. Well, what is capital R is actually the length square of the tangent vector to the curve gamma st. So it's u dot square e plus twice u dot v dot f plus v dot square g. Remember, so this is the length square of the tangent vector in the t direction. This is the first fundamental form, which is just gamma dot, the scalar product between itself. Because now, with this notation, in fact, let me keep on writing it here. So what is the length, how did I call it? The length of gamma of s, I can just phrase it like saying it's the integral between a and b of r to the 1/2. Okay. Okay, so now this is all, this is just notations, okay? Because otherwise the formula every formula becomes a blackboard, okay? Now this is the magic equation, so let's try to write down what it means. So what is d in ds of L of gamma of s? but it's the derivative with respect to S. Note that R, I stopped writing the dependence, but everything depends on S and T. Okay? So, of course, yeah. So, I take the derivative with respect to S. Here there are no issues about regularity. Everything I'm assuming is smooth and so on. So I can take the derivative and throw it inside the integrals. So, and this becomes r to the minus 1/2, the integral between a and b of r to the minus 1/2 dr ds in dt. Okay? Okay, now I ask you to believe me because, okay, we take the expression for R, imagining that everything depends on S. These are all functions of S. There is nothing mysterious here. I take the derivative with respect to S and write it there. Okay, so the RDS becomes what? Let me just give you the output. Putting everything, the terms ordered together in the way I like it. So this becomes the EDU. Because of course I will have to apply chain rule about 50 times, no? I'm taking the derivative with respect to S of a function which is in principle a function of u and v, so I take the derivative with respect to u, then times the derivative of u with respect to S. In fact, that's the way I want, exactly the way I want to group it. I want to isolate something times du ds plus something times dv ds. Okay? Okay. You can see that this is what multiplied. I mean, I take everything derivative with respect to u, and then it's multiplied by dv ds. Then everything with respect to v. Times dvds, and then you see, in some sense, what I've done up to now is just the derivative of this, this, and this, no, E, F, and G with respect to the two variables, U and V. What I'm left are these, the U dot and V dot, okay, and they contribute in the following. Let me use a little bit more of Blackboard here. It's twice E u dot plus F V dot du dot in ds plus 2, should have written smaller, F u dot plus G V dot dv dot in ds. Okay? It's actually nothing mysterious, huh? I mean, take the derivative of this, you get twice E u dot, du dot in ds, and so on. Okay, I'm just grouping it conveniently. Okay, up to now these are just brutal computations. Let's start putting into the picture something we know. For example, we know this. We know that these curves start and finish at the same point. How can I phrase it in terms of this language? For example, this translates into the conditions that du in ds is equal to dv in ds is equal to 0 at t equal a or b. Okay, because they are not moving in the s direction. Okay. So now, now it's the moment I ask you to believe me, because I need to do one step with integration by parts. We are here, huh? So imagining that we are taking this formula and we are replacing dr ds with this expression. Okay? So now my claim is just d in ds of L of gamma of S at S equal to 0 is equal to what? Is equal to an expression of this form. It's the integral between A and B of, let me call it, two functions. I need two functions I will call P and Q. P du ds plus Q dv ds. And everything is integrated with respect to t. Okay? And now, of course, I push the problem somewhere else. What are P and Q? Two parts are obvious, no? So these are long expressions, but easy to. Oh, of course, notice, I stopped here saying now I'm going to use this. How do you use it? Integrating by parts. Integrating by parts where? Here. So on these two terms I'm doing nothing. I will just now write down what are P and Q, and they will contain these two pieces in the right place. But when I go to here, I'm going to integrate by parts and throwing this d in ds somewhere else. And I'm left with u dot at the boundary and v dot at the boundary. But they vanish.
I think we do it the other way. We throw the dot to the other way. Because we have the partial by partial s. I mean, the boundary we have the partials with respect to s are vanishes. So we need in our, after integrating to get partial by partial s, so we throw the time derivative with respect to t.
Yes. Okay. It's equivalent. Well, well, the measure is dt. Okay, so if you use integral by parts, it's the t derivative which will come to that you are going to use. So I'm saying because now I'm not going to do it. Okay, I'm just telling you where you use this. Yeah, you're right. Sorry, I think now I understand what you meant. Is this dot here, which is going to be used by integral by parts. Now the dot is the d in the t, and you throw this dot somewhere else, and you are left with the boundary term du in ds, which you know it's vanishing. Okay? So now I understand. Okay. So at the end of this story, what is P? P it's 1/2 r to the minus 1/2 of what? Of dE du u dot squared plus twice df du u dot v dot plus dg du v dot squared minus, and now comes the boundary, the integral by parts term, minus, so minus d in dt of r to the minus 1/2 eu dot plus f v dot. Okay? Same thing for q. 1/2 r to the minus 1/2 times. Same thing with the v's. So d dv u dot squared plus twice df dv u dot v dot plus dg dv v dot squared minus d in dt of r to the minus 1/2, same f u dot plus g v dot. Okay? Now, just notice that these are only functions of t, because I'm already computing the derivative at s equal to 0. So everything here could make sense for s and t, but this is already at s equal to 0. Okay? So now these are only functions of t. These are only functions along the curve gamma, the central curve gamma. Okay? Now, what are we asking for a curve for gamma 0, no? Gamma has to be a geodesic if this is 0 for any possible variation. Okay? Now, so gamma 0 is a geodesic, means, this is the definition, dl ds, dl ds at s equal to 0 is equal to 0. How do I phrase it here? For example, so claim, so here, this is the claim I want to make, is if and only if p is equal to q is equal to 0. Okay, that's why I worked 10 minutes to get to that expression. Why this is true? So let's first see the easy, well, nothing is difficult, but one is easier than the other for sure. If p and q are 0, well then, what is the, remember, I shouldn't have been so quick here. I mean, this is 0 for any capital gamma, no? So what is the for any capital gamma in this formula? It's here. Remember now that we are on the domain of the chart. Our central curve is gamma here, and these are functions of u of st and v of st. Okay? Where the central gamma, of course, is given by s equal to 0. So when I say, of course, for any gamma on the surface means for any gamma on the domain of the chart is the same thing. Every variation corresponds to a variation on the chart. So basically what we are saying is anytime you change this curve in some way, in some direction, something has to happen. So what is the variable for any here? Is in the freedom of choosing these two things. Now it's du in ds which gives me the freedom. U of t is the curve, but u of s is the direction where I'm pushing. Okay? So saying that this has to be 0 for any gamma is like saying that this integral has to be 0 for any choice of these two things. Okay? So of course, if p is equal to q is equal to 0, this is 0 for anything. Vice versa. If you know that this integral is 0 for any choice of this, why p is equal to q is equal to 0? It's always it's the game that we have played with areas and with other things, no? As soon as you know, well, you can actually go both ways. You can also go by contradiction, but if, for example, p was not different from 0 at some point now it's a point in t. No? So this would be a function here. You have to think of this as a function of 0, t, because it was born like a function with s and t, but now we are already computing at s equal to 0. Okay? So suppose there exists some t naught for which this is different from 0. Then of course what do? You produce a variation. Suppose for example this is positive. I mean just to fix a sign of. Then basically what do? You construct with a cutoff function, no? With one of these functions, a variation which takes care only of this function with dv in the s equal to 0 everywhere. So basically you are just translating if one of these coordinates is, okay? And then on the u direction it just takes care of this here. Okay? So you are left with a positive integral. Just by playing with the famous functions which are 0 everywhere and they are 1 at one point, okay? Smooth. The fact that you can produce them smooth, that's okay? So it's clear why this is an if and only if. Okay? So that's very good. So we have a mathematical formulation for a curve to be a geodesic. Can I erase? Well, just this line here. So let me phrase it as a theorem so you can still see the proof. Oh, actually, the theorem is always stated in a way. Let's see if we see it right from the beginning. Okay. We have proved a general fact. Gamma, at least a curve contained in the piece of the surface given by a chart, is a geodesic if and only if P and Q are 0 on this. You see, on the other hand, this is a curve in R3, gamma is a curve in R3, so there is no harm in assuming that, for example, the initial curve to be parameterized by arc length. Why not? It simplifies a lot. So suppose gamma of t is parameterized by arc length. Now, just don't be confused. In the theory of curves, we were used to call S the arc length of a curve. Now, this is t. S is another thing now. We are not allowed to use the same name for the arc. So now t is the arc length. And gamma of t is actually contained in x of u, so that gamma of t is actually given by x of u of t v of t. Okay, under these assumptions, I have some chart which contains my curve, parameterized by arc length. Then, gamma is a geodesic if and only if. Now, what is the effect of, why did I put this extra condition? Well, it's just elegance. What does it imply in all this mess? Well, of course, the tangent vector is of norm 1, but where is the tangent vector? Here, it's here. No? Where is the norm of the tangent vector? It's the function r becomes constantly equal to 1. So in particular, in these functions p and q, forget r. Okay? So, if and only if, so the system is the following. d in dt of eu dot, where is it? I'm taking this one. eu dot plus f v dot is equal to, because this has to be 0, so I take this on the left and this one, so this becomes dE du 1/2. dE du u dot squared plus twice df du u dot v dot plus dg du v dot squared and d dt of the other thing, fu dot plus gv dot is equal 1/2 dE dv u dot squared plus twice df/dv u dot v dot plus dg/dv v dot squared. Okay? I just rewrote. Can I erase the right blackboard? Actually, after such a computation, it's always healthy to double check at least if the segment is still there. No? If this was a plane, if your surface was a plane, I mean, you prove by direct comparison that the segment is the curve of minimal length between 2 points. So it has to be a critical point. So, but what is a plane? Well, what is the first fundamental form of the plane? E is equal to 1, F is equal to 0, and G is equal to 1. So, you see that on the plane, both right-hand sides are disappearing because these are all derivatives of E, F, and G. Okay? And what you are left here, and actually, they also, for example, the first equation becomes what? U double dot equal to 0. Second equation, V double dot equal to 0. Good. Okay, so we are there. The segment is there because, of course, U double dot and V double dot equal to 0 means they are linear functions, which is exactly the meaning of being a segment. Okay? It's good. I mean, after 20 minutes of computations, it's better to at least to have one example that shows you that at least something is going in the right direction. On the other hand, before making examples, other examples, and discussing the general theory of this, what is the geometric meaning? I mean, another geometric meaning. We said, I mean, these curves are critical points of the length. So just by that, they are very interesting. But they are actually even more interesting looking at another property, geometric property. So let me phrase it in this way. Gamma is a geodesic if and only if its acceleration now, if I'm speaking of acceleration, means I'm thinking of gamma as a curve in R3. Gamma is in S, but S is in R3, so of course I can think of of gamma double dot as a vector in R3, and this is the acceleration. So if its acceleration is normal to S at every point. Okay? So in particular, the acceleration as a vector of R3 does never have a tangent component, tangential component. Okay? It's always normal to the surface. Okay? We will comment a little bit later. In a moment, let's first prove it. Okay? The notations are more or less fixed. So suppose gamma parameterized by arc length and gamma of t is actually x. There is no arm. This is actually not even local. This is pointwise. So I can assume that I'm looking at a piece of the curve covered by a chart and use the computations we did. So gamma is actually x of u of t, v of t, for some choice of u and v. Okay? So what is gamma dot? Gamma dot is u dot xu plus v dot xv. And actually, I don't even write what is the acceleration. The acceleration will be the d in dt of this. Okay? And what does it mean that it's normal? So the let me just write it in this form. Gamma dot is orthogonal to the tangent space. So this is gamma dot at t will be normal at the point gamma of t to s. If and only if what? Let me write immediately this. It means it's orthogonal to every possible tangent vector. So in particular, it has to be orthogonal to the two standard elements of the basis that we know because it's inside the chart. So if and only if. But now the vector gamma dot, I will just keep it as d in dt of u dot xu plus v dot xv. So if the scalar product between the acceleration and xu is 0, and d in dt of the tangent vector is 0. Okay? So something is normal if it's orthogonal to the tangent. Okay? Well, now the claim is that of course this is equivalent to this. Why? Well, let's expand it for a moment, this acceleration vector. So what? So in fact, it's a proof by staring at the formula. So suppose you are doing the derivative. So what do you get? You see why this is. It's not worth. So, where is this term here coming? Actually, you see, in that equation, there is one part which is clearly this. No, because every time I take the derivative, so this is the xu, it's e, xu, xv is f, and so on. So the only terms which could, well, yeah, I mean, look, I think it's almost offensive. Okay. Expand it, and you see it. It's just everything. You expand everything, and you recognize everything which is there here. Okay. Now, before again, now why this is important? Well, first of all, this is useful. It is actually useful in practice. If you have a curve on a surface and you want to know whether it's a geodesic or not, maybe sometimes instead of checking whether the curve satisfies this system of differential equations, could be just simpler to check whether this is true. Okay, because this is something you can actually do it very easily. Okay. Now, it is also philosophically very important. Actually, it's the way geodesics were actually born at the beginning. Because you see, play again the intrinsic intellectual game. So suppose you are somebody, suppose you are comparing the intrinsic and the extrinsic again. You see, our definition of geodesic was born as an intrinsic notion, because to measure the length of a curve is something I can do in my universe without taking a satellite. Okay? So I measure lengths of curves in my place, and I can decide whether such a curve is a geodesic or not. Okay. While this one is the interpretation if I can take a satellite. If I go out of my space and I look from outside, I see a curve, something moving, and I say, is it moving along a geodesic or not? Well, now I know, since I'm outside, I know what is the normal to the surface, and I can check whether this is true or not. So this is why, now that you see the conceptual difference, you also understand why this was born before, in some sense. Because, how do I want to phrase it? I mean, basically, in terms of, a physicist would tell you that motions on geodesics are motions without forces on a constrained thing. So the only constraint, so it's an inertial movement without forces, but with the only constraint that the particle stays in some place on a given surface. Okay? So these curves were actually born in physics in this way, before they were born in geometry in the other way. Okay? Good enough for philosophy. And now let's face the first question, of course. Once you get here, the first question is, of course, well, okay, but do they exist? Because up to now we don't know. Maybe we are speaking about the empty set. Okay. So, and in fact, the existence theorem is a bit more delicate than usual. Let me keep it there. So let me state it here as a theorem. Now, on the positive side, we can prove they exist. So, for any P in S, and for any V, well, V maybe it's a bad name, because it looks like one of the coordinates. Let's say psi in TPS. So for any point on the surface, and for any tangent direction, so I fix a point, and I fix one direction. Now, there exists a unique geodesic gamma from some little domain, okay, containing 0, for example, with gamma of 0 is equal to P and gamma dot at 0 is equal to psi. Okay. Now, the interesting problem about geodesic is not really whether they exist on a small scale or whether they exist on a big scale. Okay. So in fact, here the interesting question is pushed here. Okay. How big is epsilon? Okay. This theorem is just telling you there exists epsilon positive and gamma. Okay. The interesting question is usually how big is epsilon? Okay. Well, first of all, why this theorem is true in this formulation? Well, this is, I'm not going to prove it because, but I'm going just to tell you how to. So the idea is just what? This system here, so this is the system of equations we face. And the thing is that star is equivalent to another system of the form u double dot v double dot equal to, okay, where these two functions are, the only thing I really care is that these two functions are functions of u, v, u dot, and v dot. Of course, there is no second derivative on the right.
But in the star one, we have a coupled system.
Exactly. So that's my claim. Now, I'm claiming something. This is a non-trivial claim because you say, is this here? I'm saying it's equivalent. I'm not saying it's equal. Okay? Because as your colleague is pointing, as it appears here, it's not true. I mean, if I expand this derivative, this becomes something, I mean, the derivative of E times U dot plus the derivative of F times U dot, but then on the even on the first line, I have twice second derivative of U plus second derivative of V. And also here, I have second derivative of U plus second derivative of V, while here I'm claiming I can separate the second derivative of U from the second derivative of V. So there is something to be observed here. It's not immediate.
It's a linear system.
What?
It's a linear system.
It's a linear system. And what is the matrix of the coefficients of the second derivatives? E and F on the first line, and F and G on the second line, meaning the answer is it's the first fundamental form. And what is the basic property of the first fundamental form that we care? Is that it's invertible. It's a linear system whose coefficients of the two variables, now I'm thinking of this as the variables, no? So I have the second derivatives as the variables, but they appear with EFFG. And the matrix EFFG is invertible. So I can turn it into this. I mean, forget all this expression. It's a linear system and you call X and Y if you want. So when can you take a linear system with X and Y, where the X and Y are mixed, into a linear system of the form X equal to and Y equal to? Well, when the coefficients, we were taught as the Rouchet-Capelli theorem. I don't know if this is still called the Rouchet-Capelli theorem in linear algebra, but that's it. Okay? So that's the only observation, but it's a non-trivial observation. I mean, it's an accident of this kind of equation, system of equations. Okay? Now, why do I say we are throwing the problem somewhere else? I mean, so this is a kind of a cheap theorem. Okay, it's a linear system plus this observation, so there is this exists local existence and uniqueness. Okay. Now, how big is the domain of the? Oh, sorry, it's a linear system. What of second order? Maybe just one comment about. It's a second order system. So how many initial data do I have to give you to have uniqueness? Well, I have to impose U of 0 and V of 0, but this is exactly P. And I have to give you U dot of 0 and V dot of 0, and that's exactly Xi, the tangent vector. Okay? Well, can you actually, of course, the temptation is to say, no, come on. This is just because analysts are pedantic. I mean, is there global existence and global uniqueness? I mean, maybe this is a special type of system. Well, you can immediately see that this cannot be true. Again, there are trivial answers, I would say even stupid answers, and the fact that you cannot actually replace, that actually epsilon has to stay epsilon. Well, one way is to produce it by brute force. So you know the segments are geodesics. Of course, what is this theorem saying you in R2? That for every point and every direction there is a line. Well, we never proved that these are the only solutions. We actually can argue now. Okay, but for sure, in the plane, for every point and for any direction, there is one line passing with that point with that direction. Okay, so that would be, in fact, by uniqueness, this proves actually that in the plane there is no other geodesic, because that's it. There is the segment, and the segment is the unique one. Okay, so on the other hand, if you know that the segments are the only solutions in the plane, you can actually produce immediately examples where epsilon has to be bounded, because just create a hole. Take the plane and remove the origin, for example. But now, if you take what is the geodesic connecting these 2 points in the plane where you have removed the origin. Well, the point is that doesn't exist. So the point is, if I move from this point in this direction, of course I would like to draw this, but now this is not anymore contained in the surface, because at one point I have erased one point, okay? So if I start in this point with this direction, the existence theorem for geodesic has to stop here. So epsilon, just by brute force, cannot be as big as I want. Okay. That's one problem. You can produce more interesting problems. We will see some of them later. As just a final example, because I think we are almost done with time. Since example 1 is always the plane, let's see example 2, which always has to be the sphere. No? So let's see, what are the geodesics on the spheres? And actually there is no arm. I mean, nothing changes if you change, of course, the origin and the radius. But I mean, let's suppose for a moment we are taking the origin in the center of the sphere in the origin and the radius to be equal to 1. Okay. So I guess you know the answer, but let's see if our theory is compatible with the answer you know. Okay. So this is the sphere. Now, what the theorem is telling us is that if we pick any point P and any tangent direction psi, there is one and only one geodesic passing through this point in this direction. Well, how do I find it?
Must be part of a great circle because of the previous theorem we mentioned about the normal. That the normal to the surface must...
Exactly. This is, for example, one situation where the extrinsic interpretation is used. Given the fact that the acceleration has to be normal to the surface, and in the case of the sphere we know what is the normal everywhere because it's always the vector pointing at the point, you can guess the answer, which is?
A great part of a great circle.
A part of the great circle passing to this point. Let me give you another argument. So this is okay. This is one way to prove it. I mean, you have to write down a few things. I mean, this is not exactly a proof, but it will converge to a proof quickly. Let me give you another argument, because it allows me to use some interesting observation. The notion of geodesic, as we said, is intrinsic. I mean, depends only on the first fundamental form, because actually it's a property about the length of curves. So I know it's an intrinsic property. So, observation. If I have an isometry of the surface, an isometry has to map geodesic to geodesic. That's actually, I'm using this example to make you think about this thing. Okay? If you, by some accident, you know an isometry of your surface with itself, then it has to map one geodesic to a geodesic. Okay? Very good. In the case of the sphere, do I know some isometries of the sphere? It's actually one of the few cases where actually we do. For example, rotations are clearly isometries, and reflections through planes passing through the center of the sphere. No? If you take the sphere, you cut it into half, and you reflect, that's an isometry for sure. Okay? Good. So, does this give you an idea of how to find geodesics on the sphere? Well, a little bit of high school geometry. Given any point and any tangent vector to the sphere, so I claim that there exists a unique plane passing through the origin, to the center, passing through P and containing the vector Xi. So this data, the center, the point, and the vector, gives me a unique plane through the origin. Well, 2 points and the vector, that's okay, okay? Now I have a plane, and I just observe the reflection through planes to the center are isometries. So, whatever suppose I draw the geodesic that I'm looking for. The geodesic has to be, this geodesic has to be reflected into another geodesic. Okay? But what would be the tangent vector? Suppose I'm starting with a geodesic which has this tangent direction. The reflected one will start from the same point with which direction?
Sorry, when we reflect.
The same. The same, because I mean, the vector is inside the plane, so the tangent vector Xi has not changed, has not moved. So the gamma and the reflected gamma have the same tangent direction. So, are we violating the theorem? So now I have two curves, past two geodesics, passing through the same point with the same tangent direction. Of course, I cannot violate the theorem. So that means that the two reflected curves are actually not two, are the same. So the curve and the image of this curve via the reflection is actually the same. So the curve is actually fixed by the reflection. Otherwise, the theorem is wrong. See? And which is the only curve which has this property? The intersection between the plane and the sphere. The only curve which does not violate the theorem is the intersection between the plane and the sphere. It's the only one which, if I reflect it, nothing has changed. Okay? Okay, look, I have to tell you, all this is extremely lucky. In general, on a surface, on a Riemannian manifold or whatever, finding geodesics is an extremely hard task. Because really, the only weapon you have is this one. And one thing is to say that this system has solutions, and one thing is to write down the solutions. These are quite horrible. Okay, they have some little nice properties like this one. But after that, that's it, it's game over. I mean, these are non-linear in this thing here. I mean, they are linear in the top derivatives, but non-linear everywhere else, and so on. So in general, there is absolutely no general method to find geodesics. Okay? So when you can argue by geometry in this form, you are very lucky. Okay, we will see. I introduced this problem, the geodesic. I mean, geodesics are important by themselves, and also my initial motivation was to actually look for a good set of coordinates on the surface. Remember. Okay, I've been a bit more slower than I expected. So why geodesics solve also this other problem? We'll see it next lecture.